This short clip will look at nucleophilic substitution reactions with amines. To do this, we'll start with the simplest possible amine. So I've got methylamine here. As we know, it's got a lone pair, which means it can act as a nucleophile. Who might this attack? Well, here we've got a very simple little halogenoalkane. So we've got bromomethane, and we know that nucleophiles will attack in this way. Just to complete this particular mechanism, we can see that we've kicked out the bromine in the form of a bromide ion. The nitrogen is now positively charged, and it's going to lose the proton, probably by another of the amines picking that up. What we end up with then is a secondary amine, and you'll see in equations they'll include the result of the amine picking up the proton, and quite often those two will be put together as an alkyl ammonium salt. So we've made a secondary amine here. Let's think about what we've got in our reaction vessel now. So we started off with our amine, primary amine, and the primary amine has attacked the halogenoalkane, and it's produced a small amount of our secondary amine. Now, if we need to think about who's in excess. So if the primary amine is in excess compared to the halogenoalkane, there's going to be a huge amount of primary amine. So every time the halogenoalkane gets attacked, it's far more likely to be attacked by the primary amine, and therefore our only product is very much likely to be the secondary amine. However, it doesn't have to be like that. So we will see examples where actually the halogenoalkane is in excess. So we have a huge amount of the halogenoalkane, and in the first instance, yes, it will be attacked by the primary amine, and it will turn into the secondary amine. But of course, I'm sure you've noticed that the secondary amine, which is the product, also has a lone pair, which means it can also act as a nucleophile. And if the halogenoalkane is in excess, then the secondary amine will now also act as a nucleophile. See if you can complete the nucleophilic substitution mechanism for how this secondary amine will react with bromomethane. So I'll do this for you. So this is what we should get after the first step. What happens next? So we make the intermediate. We want to lose proton from that nitrogen, and we'll end up with our product. So the nitrogen, so it was a secondary before, remember. It's now tertiary. Remember, tertiaries still have a lone pair. So our product this time is now also able to act as a nucleophile if the halogenoalkane is in excess. So we go back to the beginning again, this time with a tertiary amine. acting as the nucleophile. See if you can complete the mechanism and see where you get to. Well, hopefully we've got to here. So the nitrogen kicked out the bromine in the form of a bromide ion. You can see there's something wrong with my organic product. I'm sure that you've got a positive charge on the nitrogen, and in the previous examples at this point we lost a proton to give the nitrogen its electrons back, and you might be thinking that this looks wrong and we can't do that, so it's not possible. You're quite right in thinking it looks a little bit strange, and this is the end of the road, so we can't go any further than this, but we will get to this point, and these are known as quaternary ammonium salts, and they have a use as detergents, fabric conditioners, washing powders. So these are referred to as cationic surfactants. Surfactant is a material which lowers the surface tension between two compounds, and cationic, of course, because the nitrogen in this case is positively charged, so it's a cation. And the way that it works, so these detergents need to be water soluble, which is aided by the fact it's charged, and it works as a detergent because attached to the nitrogen we probably have some longish carbon chains. These are non-polar, and these would attract the dirt or the grease.